Hello, everyone. I'm Ahmed Kosba, and I'm going to present to you our work on MIRAGE, Succinct Arguments for Randomized Algorithms with applications to universal zk-SNARKs. This is joint work with Dimitrios, Papadopoulos, Papamanthou, and Don Song. In our work, we consider the setting of zero-knowledge proofs in which a prover would like to convince a verifier that the result of applying a function f on some input x and private input w that is only known to the prover is equal to y, without leaking any information about the private input W. Recently, there have been a lot of work on a primitive called zk-SNARKs, which stand for zero-knowledge succinct non-interactive arguments of knowledge, which provide very short proofs and fast verification. In this talk, we mainly consider the QAP-based zk-SNARKs, which were introduced in 2013 and later improved in 2016 in the generic group model, which provide constant size proofs as low as 128 bytes in the generic group model, and the verification is linear in the size of the statement. This was actually attractive for many applications across cryptocurrencies like Zcash and privacy-preserving smart contracts. There are also other applications like photo authentication and certificate validation and others. However, zk-SNARKs have challenges in practice. The first one is the high proof computation cost. This led to several works on efficient circuit representations, SNARK-friendly cryptography, different optimizations in the backend, and distributed zk-SNARK proof computations. The second drawback or challenge is the trusted setup bearer computation. The prover and verifier need access to a common reference string that is generated in a trusted manner. And if this is done insecurely, the prover will be able to cheat. And if we try now to look at the zk proof systems in this space, so the first class is what I just mentioned, the zk-SNARKs that require trusted setup bearer computation, which gives us this very nice performance properties. The second class does not require trusted setup. However, the proof size and the verification effort are increased. Researchers have been also working on a middle ground. So researchers have been working on zk proof systems that require only a universal trusted setup, a single trusted setup phase that is only needed in the beginning. There are two approaches in this area. One is based on universal circuits. The most notable work in this area is the V-N-Tiny-RAM, which maintains succinct proofs and efficient verification, but it has very high proof computation costs, and the universal circuit has a quasi-linear size with respect to the number of operations. The second approach is based on universal updatable CRS. An example system, for example, is Sonic, which provides a proof of 1.1 kilobytes in its unhelped mode. There are also concurrent work like Blanc and Marlin, which also provide short proofs ranging from 400 bytes to 1 kilobyte. The contributions of our work are as follows. We aim to address the previous two challenges of zk-SNARKs by enabling randomized verification in zk-SNARK circuits and making universal circuits more efficient. In comparison with other universal zk proof systems, our universal circuit is linear with respect to the number of operations, and instead of V-N-Tiny-RAM's quasi-linear circuit. We maintain succinct proofs and efficient verification. So the proof size in our case is 160 bytes, with only 32 bytes more than Groth 16 zk-SNARK. Our proof size is 7x less than Sonic in the unhelped mode and 2.8x less than concurrent work. In terms of limitation, our CRS is not updatable, and the proof computation overhead is high in comparison with the per-circuit preprocessing zk-SNARKs. So although we improved upon the V-N-Tiny-RAM's approach and reduced the gap, there's still cost that needs to be paid for being universal. Next, I'm going to describe the details of our work. Let's first review zk-SNARK circuits briefly. So typically we start from a high-level description of the computation that we would like to verify. For example, here we have a computation that takes input from the verifier and witness from the prover. This gets translated into an arithmetic circuit of addition and multiplication over a finite field, which also gets transformed into a set of R1CS constraints. The performance of the prover typically depends on the number of constraints in the circuit or the number of multiplication gates. And the question we would like to ask here is how to support randomized algorithms. So why do we need to support randomized algorithms? Because many problems can be solved more efficiently using randomized algorithms. Examples include polynomial identity testing and primality testing. And in the case of universal C, zk-SNARK circuits specifically, randomization can help with verifying permutations more efficiently. So why is implementing randomized verification in the circuit challenging? Because if we try to implement this as simple as this, like having a randomized verification circuit that takes the problem and the solution and some random values, if we allow the prover to choose the randomness, or if the prover managed to know the randomness before computing the solution, the prover will be able to cheat. So to avoid this, we can let the prover only know the randomness after he comes up with the solution. For example, we can have some sort of hash function in the circuit that takes the problem and the solution and produces the random values needed for the randomized verification circuit. But the problem here is that this solution will have a very high cost due to calling the hash function in the circuit. So can we do this? Can we support this randomized verification without having to pay this cost? What we show in the paper is that we can do this by modifying the zk-SNARK protocol itself. And the way we do this is that we avoid the hash function calls in the circuit, but the prover will add only one group element to the zk-SNARK proof. Our total proof size is 160 bytes. And the prover will do one extra bearing and apply hash function calls on part of the zk-SNARK proofs. Typically, in the context of our universal zk-SNARK circuit, the verifier will only need 2 hash function calls. And I'm going to give a very simplified intuition here. In the zk-SNARK protocol, typically the prover computes group elements as functions of all wires in the circuit. These group elements can act as commitments. So we force the prover to do the computation of the proof over 2 stages. So in the first stage, a commitment is computed over the wires that don't need the randomness. And then this first part of the zk-SNARK proof is used to produce the randomness needed for the rest of the circuit. Of course, this has to be done carefully, and you can find the formal details in the paper. Now, the next question is how to make universal circuits more efficient. So first, what is a universal circuit? It's a circuit that accepts the program description and an assignment, and the assignment is the values of all variables, and it makes sure that the values of the assignment are consistent with the program description. For example, if we have a simple universal circuit here that supports 2 multiplication operations and 2 addition operations, it will look that way. For every operation, it needs to take the IDs of the variables that need to be multiplied or added, and also the values that will need to be checked. The circuit will have to check the correctness. So for every operation, it has to check that it has been done correctly. For example, for the first one, it needs to check that V1 times V2 is equal to V3. The second check is that it needs to verify consistency, which is that the variables that have the same IDs are going to have the same values across all the circuit. To implement step number 2 efficiently, or the second constraint here efficiently, this requires the checking permutations in the circuit. The way this was done in previous approaches like V-INTINYRAM, a permutation network was used. This has order of n log n overhead, where n is the number of operations. Using our modified zk-SNARK and randomized verification, we can reduce this cost to order of n. We also explore other issues related to universal circuit design in the paper. In terms of evaluation, in this first slide, we show how we can reduce the gap between the universal circuit approaches and the custom circuits. For example, for an application like matrix multiplication, if we have a custom circuit that supports matrix multiplication of dimension 188, using the same cost, we can support a V-INTINYRAM circuit that supports multiplication of matrices of dimension 7, according to the Buffet paper. In our case, the supported dimension will be about 40 for the same cost. Also for merge sort, we can see that we reduce the gap between the custom optimized circuit for merge sort and the universal circuit of the entire in the second setting here, we show how our approach can be used in one of the applications. So for example, in Hawk privacy-preserving smart contracts, a trusted setup was needed per each smart contract. This was one of its challenges. And instead, Mirage, the universal circuit, can be used. So in using Mirage, cryptographic keys will be generated once in a trusted manner. And for any new computation, a publicly verifiable custom verification key, about 32 bytes, will be pushed to the blockchain. This does not require a trusted setup. This can be verified by anyone. And as we show in the table here, for an application of an auction with 6 parties, 5 participants and 1 manager, of course, Hawk is going to have a better proof time than Mirage, but it requires a trusted setup for every application. When we use Mirage, we maintain the success proof and minimal verification overhead. We just have added 32 bytes to the proof and about 0.6 milliseconds to the verification time. But as I mentioned in the beginning, that there is a cost of universality that needs to be paid. The contribution of this work is that we managed to reduce this cost from the entire RAM, but there's still something that needs to be paid for being universal. So in conclusion, we presented Mirage, which enables verification of randomized algorithms in zk-SNARK circuits and provides linear-sized universal circuits. There are several feature directions, like exploring more optimizations for the universal circuit design, exploring scalability options. How can we support applications for more participants in the case of Hawk, for example, and also integrate this randomization in zk-SNARK compilers, because the randomized algorithms does not only benefit universal circuits, it can also benefit other non-universal circuits. Thank you.